So today we are going to prove the most beautiful and the most elegant equation in all of mathematics, which is the equation e to the I pi plus 1 is equals to 0. This is perhaps the most beautiful equation in all of mathematics. Everyone knows it. They have like seen it somewhere in their mathematics books or on the internet or anywhere else, or they have heard about it from someone. So we have this equation e to the power I pi plus 1 equals to 0. So you can ask like why is this equation even important to us? Why looking for its proof? Why looking for its uh, truthness? Why it is true? So for that I just want to say something. This equation have like five mathematical numbers constant in it. We have the we have the constant e, then we have I, then we have pi, then we have number 1, then we have 0. I guess you can just see from here, these are the five most important constants or numbers in all of mathematics. If you don't know about them, I want to say some words about them, like what they are. The number e, it is Euler's number. Euler's number. It represents continuous growth and its value is approximately equals to 2.71828. So, and then we have I, which is the imaginary number or imaginary unit for imaginary numbers. Which represents the square root of -1. So the letter I here, it represents the square root of -1. Then we have pi. Pi, as we all know, it's the circumference of the circle divided by the diameter of that circle, and this ratio is always equals to this number 3.14159. Oh no, these are irrational, like they never ends. Then we have the number 1 and 0. We all know about them. So you can just see how this relationship is even very much important to talk about, because it involves all these famous mathematical constants and numbers. So for the step to prove this equation, first we need to know about something very important, that is Euler's formula. This is something in mathematics that everyone studies about after, like, I don't know, maybe in their high school or later after high school. Euler's formula, it goes something like e to the power I times x is any real number, is equals to cos x plus I times sin x. Here what this means, this formula or this equation means is, on RHS we have continuous growth, which is represented by IE, and on RHS we have trig functions, trigonometric functions, and along with them we have complex numbers also. And from here we can infer that we are changing continuous growth into circles, rotations, or complex numbers. So from this equation we can see this relationship between them. So we have this formula, and if you want to know why this formula works, why is this equation even true, so for that you need to know Taylor series. This is also something in mathematics that everyone learns later on. So Taylor series for three numbers or three functions, you can say. First is e to the power x, for three functions, e to the power x, cos x, and sin x. And I don't know much about the derivation of these three functions and their Taylor series. Why is that true? Like if you ask me e to the power x is something, is equal to something, I will not be able to give you a proper explanation for that, because didn't I don't know much about that. So we have Taylor series for e to the power x is equals to uh, e to the power x is equals to 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus x4 upon 4 factorial plus x5 upon 5 factorial. We can clearly see a pattern in it as we writing it along, and this goes and on to infinity. So this is the Taylor series for e to the power x, where x is any real number. What this means is e to the power x can be written as something like this: 1 plus x square upon 2 factorial plus x3 upon 3 factorial plus x4 upon 4 factorial. Then we have the Taylor series for cos x. For cos x, the Taylor series is 1 minus x square upon 2 factorial plus x4 upon 4 factorial plus minus x6 upon 6 factorial. And similarly for sin x, we have the Taylor series for sin x is x minus x cube upon 3 factorial plus x5 upon 5 factorial. Okay, so what we have to do here is we have to in the Euler's formula we have e to the power ix is equals to cos x plus I sin x. So for that we have to obtain e to the power ix. So we can, instead of here ix, instead of in this equation we have e to the power x, we can write e to the power ix. So e to the power ix will be equals to 1 plus I times x. We just have to replace x with ix and everything will be same. Ix upon 2 factorial whole square plus ix upon ix cube upon 3 factorial plus I times x power 4 upon 4 factorial plus I times x upon 5 factorial, and on and on and on. So we can simplify it. So we have with us plus I times x plus it will be I square x square upon 2 factorial. The next will be I cube upon x cube upon 3 factorial plus I times 4 x4 upon 4 factorial plus I5 x5 upon 5 factorial. So we can see that we can simplify things here because we have I square. If you don't know, I to the power 1 is I square will be equals to minus 1. If you don't know how we got there, it's simple. I to the square is I times I, and I to the and I is under square root of minus 1, and its square will be equals to, we can just cancel it, that will be equals to minus 1. So yeah, I square is equals to minus 1. Similarly, I cube will be equals to minus I, and I4 iota, this is also called iota, so iota to the power 4 will be equals to 1. So we can substitute these values back into this equation, so we will have some nice things with us. So 1 plus uh, ix I square is minus 1, so minus x square upon 2 factorial. Here will be minus I into x cube upon 3 factorial. Here will be x4 upon 4 factorial. Here will be minus x5 upon 5 factorial. And we can now, we have with us real parts. which don't involve I with them, which are real, not complex or imaginary, and we have imaginary numbers with them, so we can just separate out these two. So before that, I guess I have made a mistake here, which is I to the power 5 will not be equals to -1, because I to the power 4 is 1, and I to the power 5 will be equals to I, because I to the power 6 will be -1. So here I will get I into x to the power 5. So now we can do we can separate the real parts and imaginary parts. So we'll get 1 minus x square upon 2 factorial plus x4 upon 4 factorial, and this goes on and on to infinity. So this is the real part. Then we have the imaginary parts with us, plus ix. Then we have minus ix cube upon 3 factorial. Then we have plus I into x5 upon 5 factorial, and these also goes on to infinity. So just one more step. And I guess now everyone can see what we are going to obtain. Here we all have I with every term I, so we can take it just common, and what we have in the bracket is x minus x cube upon 3 factorial plus xy upon 5 factorial. So we have already studied that this is the Taylor series for cos x. 1 minus x square upon 2 factorial plus x4 upon 4 factorial. This is the Taylor series for cos x. Cos x can be written in the form of this, and this is the Taylor series for sin x. X minus x cube upon 3 factorial plus x5 upon 5 factorial. So now we can write e to the power I x equals to cos x plus I times sin x. I mean, just wonderful. It's just wonderful, man. Can you see the beauty in it? We have just derived the Euler's formula. And now there is a special case where if we take the real number x here for some value, and that value should be like, must be, not must be, I think it's just a special case, we take the value just for our sake equals to pi. There is a case, just it's a case, if x happens to be pi, then what we are going to get e to the power I pi. Instead of x we get pi, and then cos pi plus I times sin pi. And we know that cos pi equals -1 and sin pi equals to 0. So if we now substitute these equations back, or substitute these values back, so what we are going to get, e to the power I pi equals -1 in place of cos x or cos pi plus I times sin pi, which is 0. So that will be equal to -1 plus 0. So we take the -1 from this side to this side. So we will get e to the power I pi plus 1 equals to 0. Boom! Wonderful! So you can clearly see that we obtained the equation. We just looked at how we got from e to the power I pi plus 1 from that formula, Euler's formula, e to the power ix equals to cos x plus I sin x, to this, the most beautiful equation in all of mathematics. So from this formula, it's not just to memorize this formula, oh this is okay, this is simple thing, this and that. No. Here what we have seen and contemplated, that all of these constants and numbers we have studied in different chapters in mathematics. like if you are reading about circles, then you will be introduced to pi. If you are studying about growth, you will be introduced to e, the Euler's number. And if you are reading about complex numbers, you will be studying or you will be introduced to I. And 1 and 0 we all know from kindergarten. So what this equation tells us that although these are coming from different chapters in mathematics, if you are just taking the school scenario, you will be studying them in different chapters, but underneath they just they are just interconnected. They share just one common language, that is the language of mathematics. So yeah, that's it.